Here's our first video getting into electrostatics, and in particular we're going to start by talking about charge. Charge, charge, that kind of thing. Okay, but not that same charge. If you haven't already, you should watch the video on Newtonian gravity, the introduction video I did on that, or some other video so that you're familiar with it, because I want to start by comparing the two. Over here, this is what's called the Coulomb force, and this is our main equation that governs all of our electrostatics. And we're not going to really cover it in great detail in this video. I'm going to do it in another video, but I want to introduce it as a way to introduce charge, Q1, Q2 over R squared. These two Q's, this is charge 1 and charge 2, and this may look familiar to you because, well, we had Newton's law of gravity, which looks like this, G m1 m2 over R squared. And so if you look at these two, they're very similar in form. Force, which by the way is a vector, is equal to a constant, Q1, Q2, and over here m1, m2 over R squared, the distance squared. And so these are very similar in form mathematically. Of course, this over here, we had this mass, which was our gravitational mass, and then we had that inertial mass, if you remember talking about that and how we discussed how these were related. Now at the time, you're probably pretty used to these two being the same thing, so you maybe didn't even understand why I was making a big deal about these two actually being related, but they are. And in fact, before this was called charge, it was actually called electric mass. Because it did for the electric force what mass does for the gravitational force. And we have these two different things. And so here's where you should really question about these two masses being the same, is because if these two masses are the same, why is the gravitational mass here the same as the inertial mass, but not the electric mass? Why isn't the electric mass related to the inertial mass? And in fact, they're not related at all. You can have a whole ton of electric mass with hardly any gravitation or inertial mass, and vice versa. You could have a bunch of this with really absolutely none of this. You can have a neutral thing like like Earth. It basically has a lot of inertial mass, but is essentially has a total of 0 electric mass. So these two don't seem to be related, yet these two are related. And again, the reason these two are related is something we'll get to later, but I just wanted you to see that in form, this charge basically acts for the electric force what mass does for the gravitational force. So charge, you should think of it as, and the way I think of it as, electric mass. It's the mass version for the electric force, whereas this was gravitational mass, so electrical mass. This was gravitational mass, and this was inertial mass. We found out these two are the same. This one, not related as far as we know so far. There are a few things that are different about this electrical mass from the gravitational mass. First, there are two types of charge, whereas there's only really one known type of mass. You either have it or you don't. But here we have what is called positive or negative charge. We have these two types of charge. And over here, again, one type of mass. What do these names positive and negative mean? Really, they're just names. They were Benjamin Franklin coined them with this, and all that really tells you is that they're opposites, that they seem to act opposite to each other, and positives act one way, negatives act another when they're interacting with each other. Again, it just shows they're opposites. Could have been named anything. It could have been named like up and down, green and blue, or Bob and Richard. I mean, it just didn't matter. The names were just there to show you that they were opposites. So it was basically arbitrary. They were functional names, I guess I should say, but have no real meaning beyond saying that they're opposites. Something that's kind of similar to mass, even though we'll later learn that mass is not conserved. You may have heard that in chemistry class, mass is conserved. It's technically not. Mass is not conserved, energy is conserved, but here we have charge is conserved. We can turn mass into energy. Maybe you learned that in chemistry, maybe you didn't. You'll definitely learn that at some point in physics. That's Einstein's old famous E equals mc squared equation. E is equal to m is in that equation, so energy and mass can be transposed, but not charge. Charge is conserved, at least it's locally conserved. That means whatever charge I have in a room, I cannot reduce or change or increase that amount of charge in the room without charge passing through the walls of the room. I either have to add it in or take it out. It can't just disappear and reappear somewhere else in the universe, or just disappear altogether. So, and really I should say that it's really the net total charge. So net charge is what is conserved, and I'll explain that in a minute when I get to it in just a second. And then the third thing is that charge is quantized. And what I mean by quantized is that it comes in very distinct specific quantities that can't be broken down any further. Kind of like if all the eggs in the world were unbreakable, then you either had a whole egg or multiples of eggs, but you could never have half an egg. And it turns out there's a minimum amount of charge that you can have. This is called the elementary charge. It's denoted with a little lowercase e, and it equals 1.6 times 10 to the negative 19th coulombs, where we're going to introduce the capital C, coulomb. This is our unit for charge, and it's named after the guy who actually came up with what is called now Coulomb's law, which is this guy up here, which we'll talk about more in another video. But the unit is the coulomb, and this was the Coulomb constant, and this is Coulomb's law, because he was very big in developing the idea of charge. He wasn't the guy that found that it was quantized. That was a guy named Millikan doing the Millikan oil droplet experiment, where he basically charged these little droplets of oil and watched them go up and down under gravity and applying electric fields to them, and was able to calculate out what the minimum amount of charge possible for a droplet was, and he found that it was this number. So that was Millikan, the Millikan oil drop. Good experiment to look into, but you basically had this little apparatus, you had this little opening, you sprayed these little oil droplets all in here, you charged them, and then you looked through this little eyepiece. I had to do this experiment, it was awful. Watched one droplet fall under gravity, and then you turn on this electric field and make it go back up and down. Charge this plate above it, and you'd watch it go up and down, figure out how much charge it had, the forces of it due to gravity, how fast it went down told you how much gravity it had on it, and then you pull it back up and you could figure out how much charge was on it, and he worked out very painstakingly what this charge was. Okay, so those are our three main differences here. There are two types of charge, positive or negative. They're just opposites. Charge is conserved locally, means you can't get rid of it, you can't destroy it. The total net charge is conserved locally. And charge is quantized, which means if you could ever measure the amount of charge you had in an object exactly, this is a really small number, then it would be divisible by this. And in fact, if it's the negative version of this, if this number is negative, it's the it's the charge of a single electron. If it's the positive version of this number, it's the charge of a single proton. And then, of course, neutrons are neutral. Okay, so let's talk about an example of charge being conserved, and then we can kind of move on from this. And essentially what I mean is total net charge has to be conserved. So let's look at something called a neutron star. A neutron star is an old dead star that has gone through its whole life cycle and it's died, and it's so massive, and there's so much gravitational force pushing in on this thing because it has so much mass that the electrons are actually forced down inside the nucleus of the atoms. So if you look at most matter, if you think back to your chemistry class, you have as many, usually, unless you have like an ion, you have a nucleus, and inside the nucleus you have protons. And typically what you have is you have the same number of electrons in orbit around the nucleus, all orbiting around the nucleus, as you do protons, which means all of the positive protons you have, the positive 1.6 times 10 to the negative 19th coulombs, are canceled out by all of the negative electrons that you have that have the negative 1.6 times 10 to the negative 19th coulombs. So if we add it all up, we get 0. So if we look at a star before it becomes a neutron star and we add up all the positive charge of the protons and all the negative charge of the electrons, we basically have the same number of each, and the star is neutral. When it crunches down into a neutron star, all of the electrons get forced down inside the nucleus, and when they get down inside the nucleus, they actually go inside the protons and they cancel out with the protons, and they cancel out the charge of a proton. And if they do that, it turns the proton into a neutron. So you have as many electrons forced down inside, canceling out all of the protons. So all the electrons cancel out all the protons, and you're left with nothing but neutrons, hence the term neutron star. And after this happens, you have lost negative charge, you have lost positive charge, but your total net charge, which was 0 to begin with when it was a full star, is still 0. So you can destroy negative charge, you can destroy positive charge, you can make them, but the total charge has to be 0. There's also a type of decay reaction that occurs, beta decay, where a neutron will actually spit out an electron. Now it was neutral before, and so you had a neutron, and then you suddenly had this negative electron. Well, what does that mean? It means that the neutron has to become a proton, a positively charged proton, so that you have this negative charge canceling with this positive charge, and you're back over here because here net charge is 0, here net charge equals 0. And it's kind of the opposite of the neutron star happening, where that occurs. Another one is when a proton gives off what's called a positive charge. It's a positively charged thing. And anyway, we can get into that later. I'm getting ahead of myself. So anyway, total net charge has to be conserved. If you have 5 coulombs of charge before, you have to have 5 coulombs of charge after. Whatever the total is, you add up all your charges in your system before. At the end of the day, all the charges in your system have to be the same. Has to total. The charges don't have to be, but the total net charge has to be the same. So if I had like 5 coulombs of charge on this object and negative 2 coulombs of charge on this object, I have a total of 3 coulombs of charge. If I were to put these together and touch them together, or shove them together into one more massive object, it would have to have 3 coulombs of charge, because these negative 2 would cancel out with 2 of these positive ones, and we'd be left with 3. So if I combine these together, push them together, I'd have 3 coulombs of charge. That kind of thing. We have to conserve the total charge. Okay. Next is transferring charge. Transfer of charge. Okay. And we're going to talk about 3 main ways to kind of move charge around. The first way is well, actually, I'm sorry. The first thing we need to do is actually tell you the 2 types of materials. We can have electrical conductors, where charge moves freely. This is typically your metals. And then we have an electrical insulator, where charge isn't free to move. These are your nonmetals for the most part. Nonmetals, like rubber, plastics, things like that. And then technically we have a third one called a semiconductor. I think there's a hyphen in that. Semiconductor. And basically what this is sometimes it's a conductor and sometimes it's an insulator. Can be either. Depends on the impurities that you put inside it. But this is what you make computer chips out of. Can be either. They basically take something like silicon, right? Silicon Valley, you've heard of it. And so you take a hunk of silicon, and in order to make the electrical pathways for all your circuitry, you dope it with impurities, which basically means you lay down impurities in it in different paths to make the different circuitries that you may want. Right? I'm just drawing in random lines to be like circuitry. So I dope and put all these impurities in that way, and I can make, when I add these impurities in it, I can make this conduct electricity through certain pathways and in certain ways. It's actually a little bit more complicated than just doing that, but the point is, you put impurities in it, and you can make it a conductor or make it conduct electricity. Take the impurities out, and it doesn't. So that's basically the idea behind that. After this, we have a few ways we can actually charge the first. So the first way to charge something is through what is called charging by contact or friction. So through contact. This is going to be your like friction, or rubbing or something, right? So this is like rubbing a balloon on your head. This is rubbing your feet on the carpet and shocking someone. Rub a balloon on your head and then your hair sticks up. Basically, the friction causes some of the electrons to move from one material to the other. So I have two different materials, like a piece of iron and a piece of wool or something, and you rub them together, right? You move them back and forth, rub them together, and electrons from one will jump over to the other, and so you had two neutral items before, and you end up with, after the rubbing, they were neutral before, you end up with one object being positively charged and the other being negatively charged because the electrons transferred one to the other. You move the protons there inside the nucleus, so mostly it's the electrons that are the charge carriers. They're the ones that are moved through this transfer of charge. And you end up with something positive, something negative. And then one of the things we'll learn later is positives and negatives, they attract, and that's why you rub the balloon on your head and suddenly your hair attracts towards the balloon, because one's positive, one is negative through this. The second way is through induction, and this involves charging a conductor. And so the idea is, if I have a conductor that's sitting here, like say a metal ball, has as many positive charges on it as negative charges floating around inside. It's a conductor, so they can move, the negative charges can move all around freely. And what happens is, I'm going to bring another object near it, say something that's negatively charged, right? So it doesn't matter what this is, but you bring it near here, and the positives attract to negatives, but the negatives repel from each other, right? Like the old opposites attract thing. So these negative charges here will actually repel these negative charges here that are free to move. And so what will happen is these little negative charges will repel away, and they'll move as far away as they can, and they'll get over here. And so at this point we have a separation of charge. If we then do something called grounding, and this is the symbol for it, these three little lines like that, grounding literally means hooking something up to the ground to Earth. We can treat Earth is so big compared to our electronics and stuff and our size that we can basically treat it as a place that we can shove as much charge into and take as much electrical charge or electrons in and out of as we want, like it's infinite source or pool that we can shove electrons to. So we put this ground here, and these electrons, they want to get as far away from these other electrons as they can, so they start traveling down the ground wire, and they go literally into the Earth, into the ground, the planet, right? So all these negative charges, they go off and leave, right, which makes this positively charged. I could then disconnect this ground wire so that none of the electrons can come back, right? I kind of erased my positively charged. I could then remove this negative charge here. I don't even need it anymore. And what am I left with? I'm left with just this one electron, this one negative charge, or however many it is. I'm left with less negative charges than I am positive charges, and this becomes positively charged. Okay? This is a positive charge now on this thing that was neutral before. And I could have done the opposite. I could have charged it negatively by putting a positively charged rod there, attaching it to ground, and then essentially what it would do is allow extra electrons to have come back up on here, because the electrons would have attracted to the positive charge here, it would have allowed extra electrons to come up through the ground and get on here, disconnect the ground, and I'd have something that was then negatively charged. It would have more negative charge. But basically I put a negative charge, or I put a negative charge near it, and I can charge it positively, put a positive charge near it, and I'll charge it negatively. So this will charge something into the opposite of whatever you bring near it. Okay? Rewind, watch that part a couple times, and see if you can figure out how, try and go through and do the whole, here's my positively charged rod, here's my neutral, my neutral object here. See if you can go through and tell me what would happen. Remember, the positive charges don't move, just the negative charges move. So if something is positively charged, it means it has too few electrons. If something is negatively charged, it means extra electrons. So remember, these negatives are going to attract over to this positives. And so if we attach the ground to this, try and go through and say what would actually happen. What would happen, and you should end up with this ends up. Once you remove the ground and remove this positive charge, it should be negatively charged. So see if you can walk yourself through how that would happen. Okay, the third kind, or the third way that we're interested in charging something is through something called a surface charge, R, surface charge. And this is basically doing the same thing as induction. So it's induction with an insulator. So over here, the charges could actually move and leave the conductor, but on an insulator they can't do that because they're not free to move. But they are free to slightly rearrange. If you look at an atom, so let's just say here's our nucleus, and then we have the charge, usually the electrons, they're kind of evenly distributed around it. But if we say put something that was negatively charged here near this atom, what's going to happen? It's going to repel these negative charges. So these negative charges are going to move over, or want to tend to stay on the far side of the electron, which means that we would have a more positive side over here and a more negative side over here, and we would have this separation of charge. And so if we looked at this, with two objects, like say I, had a charged balloon here, right? So I have a balloon, and let's say the balloon is positively charged overall. I can't remember if balloons charge positive or negative. I can't remember, but anyway, let's say we had this positively charged balloon, and then we brought another piece of plastic or piece of something, little pieces of paper or something near it. Well, what would happen? What would happen is it would be the opposite of what I drew here. The electrons would transfer to this side, and so in each atom that we'd have, each molecule, oops, I drew the wrong thing. In each molecule, if we zoomed in, like microscopically looking at it, we'd say we'd have a negative side and a positive side. They would separate like this, negative, positive, negative, positive. And overall, it would create a little attractive force between them. So it would attract because the negatives are slightly closer to the positive object than the positives are. And if you remember from Coulomb's law, force is proportional to 1 over the distance squared. So the ones that are closer are going to have a stronger electric force than the repulsive force of the ones that are further away, and you get a slight attraction. Sometimes you could do this to, like, you rub a balloon on your head and you put it down near like some light confetti or something, and the confetti will attract up to it. And it's because of this surface charge happening with these things. Okay? So make sure that you're kind of pretty familiar with these 3 types of charging mechanisms. Maybe rewatch the video a couple times to make sure you understand what I was talking about and all these things. And I think that's pretty much going to be it.